Hi, my name is Francis Arce, and today my presentation will be on red snapper in the Gulf of Mexico, so juvenile red snapper stock structure analysis within the Gulf of Mexico through otolith elemental chemistry and morphometrics analysis. So the purpose of this study was to establish a clear foundation for a second year project for a research master's degree in my second year. So the topic of red snapper has been a widely discussed issue within the Gulf of Mexico. Since the late 1980s, red snapper has continued to be an exploited overfish species within the Gulf of Mexico among fishermen. Considered as being the second most important fisheries area in the United States, the management of red snapper in the Gulf of Mexico is vital. The stock population of red snapper is under constant threat from combined pressures by commercial and recreational fisheries. Due to the industry of fishery, shrimp trawling, operating in juvenile red snapper habitats, excessive bycatch mortality along with commercial and recreational fishing exploitation has led to the 90% diminution in biomass since the 1970s. For well over a decade, the red snapper population in the Gulf of Mexico has been considered overfished despite the implementation of restrictive fishing regulations in the 1990s. Knowledge of population structure and dynamics has enhanced the understanding of red snapper ecology over the years. So the aim for the final project is to identify which method of otolith analysis is most effective at identifying stock structure of juvenile red snappers within the Gulf of Mexico. The two methods which I will be looking at to analyze the otoliths will be otolith elemental chemistry using the chemical element barium and morphometrics, which is a shape morphology study. My research questions so far are of the two following. So which method can reliably identify the origin of juvenile red snapper? Otolith elemental chemistry analysis or morphometrics analysis, so it will be a comparative study. And then the other one would be can stock structure patterns of red snapper juveniles be determined when comparing east and west regions of the Gulf of Mexico through otolith elemental chemistry and shape morphology analysis. So red snappers are a reef-associated demersal species. They are commonly abundant and distributed along the continental shelf and slope. Juvenile snappers are normally found distributed in unique habitats like estuaries. They usually favour low relief sands, small-scale artificial reefs within their first year of life. The image shown just explains the deterioration of red snapper stocks and how it has led to not only declining population numbers but also declining biological characteristics in the species. Adult snapper catch average weight, size, age and reproduction has significantly declined. In 1962, catch consisted of more older and mature snappers being larger in size. However, with the progressing years, they have decreased in size and age. This decline hinders the repopulation of snappers as their reproductive capacities have declined due to typically the older snappers were the ones who produced the more eggs. So otolith analysis is used and is a calcified structure within the ear bone to allow the fish to balance and orientate. It is considered as a natural tag as the otolith is metabolically inert, allowing for chemical element signatures within the core of the otolith. Applying them as a natural tag in other fish species to assess nursery source regions suggested that it may be beneficial to use the same method in red snapper in the Gulf of Mexico. Otolith chemistry has been widely acknowledged as the most effective tool determining fish migratory patterns and potential contributions of juveniles in certain nursery areas. Through the chemical signatures displayed within the otolith core, recruitment patterns, population stocks and spawning locations can essentially be determined. This is achieved by comparing various samples and distinguishing similarities and differences among the otolith. Where there are similarities in chemical signatures across otolith, one can assume that they come from the same or similar population stock and vice versa with spawning locations. So in the study, barium will be the main chemical element which will be analysed. It will be used to identify the similarities between different red snapper otoliths. So these chemical elements will identify the migratory patterns and possibly let us know what population is supporting the larval recruitment in the Gulf of Mexico, which is crucial for understanding the stock structure of red snapper in the Gulf. So morphometrics has been used as a tool to analyze the morphology of fish otoliths, widely used as it recognizes that each species otolith has a distinct form and characteristics seen within the same species. Therefore, morphometrics is commonly used within studies to determine geographic regions between various substocks of fish species. The variation of shape among otoliths has assisted in distinguishing similarities and differences between species stock populations.
Hi, so I'm just going to show you how I go through my methods for this project that I'm doing this presentation. So first of all, I received my otolith samples from America through Sandra Diamond. So she receives them from the TPWD, the Texas Parks and Wildlife Department over in Texas, America. And what I get is just the otolith itself. So it's like a really tiny little bone. So it's just like a ball. And what I have to do is I have to embed it into some epoxy resin. So it's just a mold. So once it's embedded into the resin, it turns out like a little tablet like that. It's really tiny, and the otolith is right inside. So with this, what I do is then I put it through this blade. So just for demonstration, I'm not going to turn it on, but if you look here, there's a tiny gap in between these two blades here that are side by side. So what I want to do is I just put the resin mold in here, and then I'll move it down while this blade is spinning, and it will just cut right through the middle of that otolith. So what I'm hoping to get is, in that cut that I get, I want the core, and because the core is what I'm going to be analysing. So once I do have the core, I get this tiny little cut like this, and I just glue it onto this slide. This slide has been cut, so it's much smaller than what it was before. But yeah, so it's just glued on there, and then once I have it glued on there, I just have to look under the microscope and try and see if I've actually gotten the core. So what the core would look like is a tiny little peanut figure sort of thing. So it's just a dot, like right in the middle. It should be in the middle. Sometimes they're not in the middle, but that's what I'm after. Okay, so once I have my cut glued onto the slide, I want to get closer to the core as I possibly can. So by doing this, I have to polish it. So I just use this aluminium oxide powder. So it's just like this. So this is the 20 micromil one, and then I've got 4 pads. So one's for the 20 mil, one's for the 3 micromil, one's for 0.3 micromil, and the other one's for 0.05. So what I do is I just put some onto the pad, I mix it with water, and then I just mix it together to get the right consistency that I want. Once I do, I just put the slide face down, and then I start moving in a figure 8 motion like that, and that just polishes it down. So if I see that my core is closer to the bottom where it's stuck on the slide, I'd use the 20 micromil, because that would take off more surface. So it'd get rid of more of the top layer and go right down to the core. And then when I see that I'm about to reach the core, I start polishing it off just to get a smooth surface, a clear smooth surface. And I'd use the 0.3 or the 0.03. I'd more likely use the 0.05, because it's more gentle and it's safer, because I don't want to blow the core. And then, so once that is done, I just take it over to the microscope in between every measurement that I go down, just to make sure that I'm on track and I'm getting closer to the core instead of blowing it off. So it's a really, really tricky task to do, because you have to be very precise and very gentle with how much you're actually polishing off the surface, because it's because obviously you can't get the same sample again over and over if it's one fish. So you'd have to be really, really gentle and careful. So once I have my sample ready and it's like as close as the core that I can possibly get to it. I'll have to go to UTS to use the ICP-MS laser there. So it's just a laser which it shoots like lines through the sample to collect all the chemical components that are stored in the bone, and through that I can begin my analysis.
So once all the polishing is done, it will go to UTS, and on the slide through the laser ablation inductively coupled mass spectrometry to receive images of the chemical components which is stored within the otolith. So these images will display the otolith and any chemical component which the laser has picked up on, and it is analyzed through a program called Miyavi and iSatis. The program allows for these chemical components to be depicted through a image. So once again, red snapper juvenile otolith samples are obtained through Texas Park and Wildlife Department and from the National Oceanic and Atmospheric Administration Agency. Juvenile red snappers will be from 2009 samples and are to be 70 to 120 days of age. Samples will range from both west and east regions of the Gulf of Mexico. The red snapper otoliths were caught from spawning grounds in the Gulf of Mexico. Red snappers caught were of age 70 to 120 days of age. Measurements of otoliths lengths as well as total length of the fish were taken at the time of catch. So following from the methods of preparing the otolith from above prior to being placed through the laser ICP-MS laser machine, otoliths will be put through a light microscope to be aged. The age is identified by counting the amount of rings shown on the otolith. Once this has been completed, the otolith will follow the methods as described in the otolith elemental analysis methodology. This is to obtain the image outline of the otolith to then be analyzed for its shape morphology. Morphometric software will be installed to begin analyzing the otolith. However, the software which will be used is yet to be chosen for the final project, as there are many out there. The main aim of the study was to scope and establish a clear research aim for the project. There was no actual data generated from this study. However, previous data which had been recorded were analysed to create a sample size. Previous samples that were collected are from 2009, consisting of juvenile red snappers distributed across the whole Gulf of Mexico. The comparative study between otolith elemental chemistry and morphometrics will determine which methodology is favoured. The assumption at this stage is that otolith elemental chemistry will be more of a popular methodology over morphometrics. The weakness with morphometrics is based on the limitation of analysing only the shape morphology. So really the study aims at comparing the methodology of the two otolith analysis techniques and how efficient they are at producing the most descriptive data there is. Although both analyze the otolith, they analyze it in a different way. Otolith elemental analysis identifies patterns with red snapper stock structures by measuring elemental chemistry such as the presence of certain chemical elements like barium present within the core of otoliths. Chemical elements present in waters of red snapper migration routes are absorbed into the otolith and leave chemical signatures behind, whereas the study of morphometrics measures the shape morphology of otoliths in red snappers. Those with similar shape morphology are assumed to be derived from the same origin or are connected with the same stock. However, based on discrimination, there is the assumption that otolith elemental chemistry will be the favourable methodology over morphometrics analysis. Otolith elemental chemistry is able to determine various factors such as spawning regions, nursery sites, preferred habitats and migration patterns, whereas morphometrics is limited to only displaying the characteristics of otolith shape morphology, which assists in identifying common inhabited environments within the study. Also, I looked at an unpublished study which was conducted in an undergraduate degree by myself I used it as a guide to design the methods in this research project. So the study found clear differences of barium in otolith samples from 2009. Those which appeared to be different were observed to be caught in different areas throughout the Gulf. Samples with similarities were within close proximity to each other. However, this was part of a small sample study. There wasn't a lot of samples available, which made discrimination again among the samples very limited. Yeah, in the years I also studied were 2010 and 2011 samples, and the trends which were found were actually in reverse to the trends I found in 2009, which supported Goodyear's hypothesis that red snapper was stock mixing, that they were stock mixing and basically mixing with other little sub population groups. So Goodyear had also suggested that although red snapper is believed to be functioning as a single unit stock by the Gulf of Mexico's Fishery Management Council, there may be substock populations mixing. So historically, red snapper has always been managed as a single stock species within the Gulf of Mexico. Additionally, red snapper preferred habitats are still unclear, and with the further advancement of otolith analysis, preferred habitats along with recruitment patterns and spawning locations can be identified. Thus, the importance of further research using otolith analysis is essential for the management and sustainability of red snapper in the Gulf of Mexico.